When Volta made the first battery, he used different hardness of metals, one softer on harder, to make a pile of metal discs, linking them together with paper soaked in acid. The relationship between softer and harder metals gives a difference in voltage when these metals are in contact with one another. What other combinations of metals could be done for other more power types of metal contact batteries? ChatGPT. Volta's battery, the voltaic pile, relied on the electrochemical difference between metals, which created a voltage potential when in contact with an electrolyte, the acid-soaked paper. The key to developing more powerful batteries lies in selecting metals with larger differences in their reactivity and optimizing the electrolyte. Here are some alternative metal combinations that could provide different voltages or power types for metal contact batteries. 1. Magnesium and copper. Electrode potential difference. Magnesium is highly reactive compared to copper, creating a greater potential difference. Applications. Magnesium is lightweight and has a high energy density, making it ideal for high-performance batteries. 2. Aluminum and graphite or carbon. Electrode potential difference. Aluminum is more reactive than graphite, offering a relatively high voltage difference. Applications. Aluminum is abundant and cheap, making this combination promising for cost-effective batteries like those in aluminum-air batteries. 3. Lithium and copper or carbon. Electrode potential difference. Lithium is extremely reactive and used in modern batteries like lithium-ion. Applications. Lithium-based batteries provide high energy density and are common in portable electronics and electric vehicles. 4. Zinc and copper. Electrode potential difference. This combination is widely used in simple batteries, like the classic copper-zinc galvanic cell. Applications. Zinc-copper batteries are relatively safe and used in devices such as flashlights and simple electronics. 5. Zinc and silver. Electrode potential difference. Silver is less reactive than copper but offers higher conductivity, and paired with zinc, it can create batteries with more stable voltage. Applications. These are used in high-end batteries for medical devices or small electronics requiring stable, reliable power. 6. Iron and nickel. Electrode potential difference. Iron is moderately reactive and nickel is less so, but the combination works well in nickel-iron batteries, Edison cells. Applications. These batteries are durable and have long lifespans, ideal for industrial applications or renewable energy storage. 7. Tin and lead. Electrode potential difference. Tin and lead have been used historically, especially in lead-acid batteries. Applications. These batteries are robust and widely used in automotive applications, although they are heavy. 8. Calcium and copper or carbon. Electrode potential difference. Calcium is another reactive metal that could be used to replace more common metals like zinc or aluminum. Applications. Calcium-based batteries are in development for their potential to provide better energy density than traditional systems. 9. Nickel and cadmium. Electrode potential difference. Used in older rechargeable batteries, nickel-cadmium cells provide reliable performance. Applications. Though less common now, nickel-cadmium batteries were once popular in power tools and electronics due to their rechargeability and longevity. Factors to consider for more powerful batteries. Larger potential difference. Choosing metals farther apart in the electrochemical series, such as lithium and fluorine, though difficult to stabilize, gives more voltage. Electrolyte optimization. Stronger or more efficient electrolytes can enhance the performance, such as using lithium salts, potassium hydroxide, or organic electrolytes. Environmental stability. The metals should not corrode quickly, which can degrade battery performance. Experimenting with combinations of more reactive and less reactive metals while using advanced electrolytes is the key to creating higher performance batteries. The challenge lies in balancing energy output, stability, cost, and environmental impact.
Okay, well, there you have it. That's what ChatGPT thinks about battery construction research. These are the different combinations of metals. Some are already used, some I don't think are used, but this is the list of different contact metals that you could make, just like Volta did with his voltaic pile. You could stack these and make a pile of these metals paired together, and stack them over and over and over on top of each other and see what kind of voltage you get out of a pile of metal with combinations of these types here. And it says that experimenting with combinations of more reactive and less reactive metals while using advanced electrolytes is the key to creating high performance batteries. And the challenge is balancing out the energy output with stability and cost and environmental impact. So, the best thing to do would be to pick metals that don't corrode, that corrode the least, like aluminum. Aluminum, I don't think corrodes very easily, and or aluminium, however you want to call it, aluminium, aluminum, or aluminium. Um, and you'd want to try to combine that with something else that doesn't corrode. You want to, like, I would think that non-corrosive battery metals would be more important than having metals that do corrode and go bad that have like better performance. I'd rather have batteries that don't corrode and are long lasting than to have batteries that need to be replaced all the time, like these golf cart lead acid batteries that I have to deal with all the time. They the like if any like it like on the inside, the metal plates, the metal can get to a point where it gets soft and it can crack or fracture or anything like that, and it can cause a short circuit inside the battery, where there'll be a spark in between the gap where the crack is in the metal plate, and that could cause a hydrogen gas to get ignited inside the battery and cause the battery to explode. So, um, lead acid batteries to me are not very ef- um, efficient because they can be fracture easily, they can explode, they're not very safe. But if you had two different types of metals that were fairly strong, that made electricity, that didn't corrode, that you could make abundance of, like aluminum is very abundant, would be one choice of metal, okay, because it doesn't corrode very easily. And then something else for contact electricity with aluminum, like he said, it says aluminum and graphite or carbon. And I'm thinking the electrolyte, instead of making it acid, like like battery acid with water, why not do the same thing that um, they did for the coherer? Make a bunch of metal filings, make a lot of metal filings, and grind these something very conductive, a very conductive metal, and grind that into very fine filings, and then put that into the water. Well, I guess they would all sink to the bottom, wouldn't they? Um, well, what about something like mercury? Instead of lead acid, instead of acid mixed with water, why couldn't you have something like mercury, a liquid metal that's in there that's conductive? Could you have a liquid mercury of lead acid? Would that work as a battery? Uh, Now that's my line of thinking. Like I wouldn't want a acid liquid for the electricity to pass through. I would want two materials, like one liquid metal, one non-liquid metal and have electricity pass between both of them naturally, and then tap the power as the energy is passing between the two types of metal. Like to have, one type of metal plate, another type of metal plate, and have the battery acid solution for the electricity to pass from one metal plate to the other, and that doesn't make sense to me. But anyway, this is what should be done for global battery, national global research for batteries and renewable battery storage. Energy storage research for batteries right here. Metal combinations for piles of metal battery prototypes.